أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم Alhamdulillah, thanks for Allah subhanahu wa ta'ala for all his blessings and bounties that he has bestowed upon us. فَبِأَيِّ آلَاءِ رَبِّكُمَا تُكَذِّبَانِ. Today we are going to talk about a new topic. If you remember in the last lecture, we ended up talking about Laplace transformation. No, we are going to talk about partial differential equations. Initially, we started off talking about ordinary differential equations. Now we have to move on to partial differential equations. They are closely resembled with each other. Because behind the scene, there is a time-dependent phenomena. On top of that, time is going to be a continuous variable. So it will turn out to be differential equation from the time-dependent phenomena to the mathematical formulation. We will be having differential equation. Just like if you remember from calculus, we discussed ordinary and partial derivatives. So the derivative with respect to only one independent variable. In case we have a function of only one independent variable and we are interested to find change, so it will turn out to be ordinary derivative. But in the case of a function of more than one variables, now we have more than one options to move around. Just like if you look into the chain rule, the schematic of chain rule. So we have two branches over there. We have two options now. Either we can move in the direction of x or y. For example, if the function is having two independent variables, x and y, so then we have the liberty to find the change in the dependent variable either with respect to x or y. So when we move in the direction of x or when we obtain change in the dependent variable with respect to x, this is not going to be complete change. It's a partial change. So this is how we say that we partly differentiate. So this is how eventually we will be having the concept of partial differentiation. So based upon the concept of ordinary differentiation, we move on to ordinary differential equations pretty much on the same line. Whenever we have a function of more than one independent variables, the phenomena is such in a way that we have a function of more than one independent variables, then the mathematical formulation will turn out to be partial differential equation. So keep an eye, the difference between ordinary and partial derivatives. We are going to talk about partial differential equations. So surely it is going to be a differential equation, but because of the name partial, so we are expecting that the dependent variable is going to be a function of more than one independent variables. So before we move on, we have to talk about the foundation. We need to talk about some basic elements of partial differential equations. Few words about partial differential equations. We say that they arise in connection with various physical and geometrical problems when the function involved depend upon two or more than two independent variables. So these variables may be a temporal component, means time, or spatial components like space coordinates x, y, z. So we are going to talk about a problem when the function involved depend upon more than one independent variables. So we will look into the basic elements related to partial differential equations. We also look into the formation and the methods for finding solutions of partial differential equations. And on top of that, very vital, very Important technique available to find the solution of partial differential equations known as method of separation of variables. We already have gone through with that. In the case of ordinary differential equation, first order. Now we will also look into the method of separation of variables, slightly different from that version. Because now we are going to handle the concept of partial differential equations. So these are the main topics that we need to talk about: basic elements, formation, and then the techniques available. How do we find the solution of various partial differential equations? So we take start talking about the definition. What the definition of partial differential equation is. So we see that a partial differential equation is going to be an equation, of course, surely, involving partial derivatives of a function of two or more than two independent variables. If you kindly switch off your microphone, all of you. Let me double check. All right. So there is going to be a differential equation, but since it is going to involve partial derivatives of a function of two or more than two independent variables. So what are the elements to be there when we describe our differential equation known as partial differential equation? So we say that a partial differential equation in the dependent variable, for example, u, and independent variables like x, y, z, and t, is the relation of this particular form. So we will be having dependent variable symbolically u, we will be having independent variables symbolically x, y, z, and t. So how do they are connected with each other? How they've been described? They are going to describe a relation between them. So we say that we will be having all sort of elements over there: dependent variable, independent variables, and their partial derivatives. Of the dependent variable with respect to x, one of the independent variable, y, one of the other variable, or with respect to z, another one with respect to t. So these are all sort of partial derivatives of the dependent variable with respect to x, y, z, and t being the independent variables. Not only the first, but also there could be a chance of having higher order derivatives like u, xx, u, xy, u, xxx. I mean, these are the symbolic representations, subscript notation, and we already have gone through with that idea. When we talk about partial differentiation, when we talk about the derivative of dependent variable with respect to more than one independent variable, sometimes it is more viable to have this subscript notation. So ux means it's a partial derivative of u with respect to x, keeping all the other variables held fixed. So when we talk about the partial derivative of u with respect to y, it means that all the other independent variables are going to be held fixed. If we have four of them, like x, y, z, and t, then with respect to y means x, z, and t, they are going to be held fixed. Take an example. Particular expressions are there. So you see that it's a relation between u, dependent variable is there, independent variables x and y, and their first partial derivative of u with respect to x and y. In the second example, partial derivatives of x of u with respect to x and y are there. So these are the examples of partial differential equations. We say that they are partial differential equations because they involve dependent variable u and its derivatives, but not the derivative. Now the derivatives are going to be partial derivatives. So this is how the equation is going to be partial differential equation. Just recall the basic concepts about the order and degree of a non-linear differential equation, pretty much on the same line. The order of a partial differential equation is the order of the highest partial derivative that occurs in the given differential equation. So the order of a partial differential equation is going to be pretty much the same idea. And the degree, again, the same idea. The greatest exponent of the highest partial derivative is going to be the degree. For example, if you look into equation number 6 in this text. So for number 6, we see that the highest derivative is of order 1. So equation number 6 is of first order. The highest derivative in the second example is of order 2. So second example is an example of a partial differential equation with order 2. The greatest exponent of the highest derivative. So we see that the combined power of the first derivative is 1 in both cases. So we say that equation number 6 is of first order and first degree partial differential equation. Second one is of second order, but the combined power is 1 in both cases. So this is all, the degree is going to be 1. Example number 6 or equation number 6 is an example of a partial differential equation of order 1, degree 1. Equation number 7 is an example of a partial differential equation of order 2, but degree 1. Whereas if you look into this example, equation number 8, so order is going to be the highest derivative. So we see that, yes, this is the third. So we say that equation number 8 is an example of a partial differential equation of order 3. And then degree is going to be the exponent or the power of the highest derivative. So we see that the combined power of the highest derivative is 2. So equation number 8 is an example of a partial differential equation of order 3, but degree 2. Linear and non-linear partial differential equations. So again, I mean, non-linearity is going to be very vast area to be discussed. We also look into the intensity of non-linearity. Sometimes non-linearity is not that much intensive. Sometimes it's mildly non-linear or highly non-linear. Quite a few things are there. But simple idea is there. When we talk about the partial differential equation, on the basis of those characteristics, we can easily observe whether the equation is linear or non-linear. So we say that a partial differential equation is said to be linear if it is of the first degree in the dependent variable and all of its partial derivatives, pretty much the same. Criterion. One of the criterion, as we have discussed in the case of ordinary differential equation. If second one, if the coefficients of the dependent variable and its derivatives are functions of only of the independent variables. You see that in this example, the coefficient of partial u upon partial y is a function of the independent variable. Coefficient is again independent variable. What about the coefficient in this case? It is going to be, I mean, the constant could be taken as function of x, could be taken as function of y, like x raised to power 0 is 1, y raised to power 0 is 1. So again, keep an eye. If the differential equation is of the first degree in the dependent variable and all of its partial derivatives. Secondly, the coefficients of the dependent variable and its derivatives are functions only of the independent variable. So we say that yes, it is going to be linear. Otherwise, it is going to be non-linear. Have a look at example number 6. So should be degree 1 there should be degree 1. Yes, example number 6 and 7, they are of degree 1. So we can consider them. Second property, the coefficients of the dependent variable and its derivatives are functions only of the independent variable. Yes, we see that. Dependent variable, coefficient is there, coefficient is there, coefficient is there, coefficient is there, coefficient is there. So yes, equation number 6 and 7, they are examples of linear partial differential equations. But if you look into example number 8 or equation number 8, in this example, since equation is non-linear, so we cannot look into the second aspect where we have to keep an eye on the coefficients. Since it's non-linear, so the very first thing, it's non-linear. It is non-linear. Equation number 8 is non-linear because the degree is going to be greater than 1 because of the first property is violated. It should be of degree 1. So since we see that equation number 8 is an example of a partial differential equation with degree 2, so it is not going to be linear. So example in equation number 6 and example in equation number 7 are linear, but example in equation number 8 is going to be non-linear. Homogeneous and non-homogeneous we have gone through. And remember, same wording has got different meaning in different context. We have discussed homogeneous, first order, higher order, homogeneous and non-homogeneous ordinary differential equations. Now we are going to talk about partial differential equations. So very first thing, before we look into homogeneous and non-homogeneous, we need to keep an eye. A linear partial differential equation is going to be homogeneous. So first of all, it has to be linear. If it is non-linear, get rid of them. If it is linear, then further we need to check if each term in the equation contains either the dependent variable or one of its derivatives. So a linear partial differential equation is said to be homogeneous if each term in the equation contains either the dependent variable or one of its derivatives. Every term there should be either the dependent variable or one of its derivatives, no matter what the order of the derivative is there. Otherwise, it is said to be non-linear or inhomogeneous partial differential equation. For example, if you look into equation number 6, so the very first thing that we need to keep an eye that the equation should be linear. Only then we can look into the homogeneous and non-homogeneous discussion. So we see that equation number 6 is linear. Equation number 7 is the linear. On top of that, if each term in the equation contains either the dependent variable or one of its derivatives, so we see that yes, equation number 6 and 7, both criterions are fulfilled. Number 1, they are linear, 6 and 7. On top of that, every term does contain, every non-zero term does contain either the dependent variable, you see, yes, or one of its derivative. To the left hand side, we have two first order derivatives. We have second order derivatives. So yes, equation number 6 and 7, they are homogeneous. We cannot talk about equation number 8, remember, because it's non-linear. So the very first thing that we need to keep an eye while talking about homogeneous and non-homogeneous, the equation should be linear. Only then we can look into the consideration whether it is going to be homogeneous or non-homogeneous. If you look into this example, we see that in that equation, yes, The first term to the left hand side does have dependent partial derivative of the dependent variable. Second term in the equation does have, but to the right hand side there is no dependent or its derivative. So what the condition? If each term in the equation contains either the dependent variable or one of its derivative, only then we say that it is going to be homogeneous. Now closely look into this equation. We regard that one as non-homogeneous, but have a look at this example. Equation number 6. Pretty much the same structure is there. The right hand side is non-zero, but you see that we are having dependent variable. Derivatives are there to the left hand side. No problem with the left hand side, but since the right hand side is independent of the dependent variable, so this is how we say that it is going to be non-homogeneous. Condition is that first of all should be linear. Yes, it's linear. On top of that, every term contains either the dependent variable or one of its derivative. Yes, derivative is there, no trouble with the left hand side, but since the right hand side is independent of the dependent variable and is also independent of the derivatives of the dependent variable, so this is how we say that it is going to be non-homogeneous. General and particular solutions. So pretty much the same idea that we have discussed while talking about ordinary differential equations. So general solution is a solution having as many arbitrary constants as the order of the differential equation while talking about ordinary differential equations, and the solution obtained from the general solution by giving particular values to those arbitrary constants is going to be a particular solution. So pretty much the same idea. A solution of a partial differential equation is any function which satisfies the equation identically. Surely it has to be a solution. Then we are going to talk about general and particular solution. Solution means not only the value in terms of expression of the dependent variable, but all sort of derivatives involved in the equation, they should be satisfied, or the equation should be satisfied identically. If you plug in all these things in the equation, so equality must hold. The general solution is a solution which contains the number of arbitrary independent functions now equal to the order of the equation. So remember, pretty much the same idea. Over there, in the case of ordinary differential equation, we talk about the number of arbitrary constants. Over here, we are going to talk about number of arbitrary independent functions. If this number is equal to the order of the equation, we say that the solution is going to be general solution. And particular is the one obtained from the general solution by particular choices of arbitrary functions. Normally, we apply certain conditions over there to obtain those arbitrary functions in the case of partial differential equations. So in this way, we will be having a particular solution. For example, it can be observed clearly from this expression u. So you see that independent variables x and y, dependent is u. So f of x is an arbitrary function of the variable x. G is another arbitrary function of the variable y. So u is going to be a solution, since behind the scene we will be having an equation of this form. It's a second order, so we have as many arbitrary independent functions as the order of the equation. So we say that this one is going to be a general solution of that equation, since it contains two arbitrary independent functions f and g. So it is called as general solution. On the other hand side, if in particular f of x is 2 sine of x and g of y is 3y raised to power 4 minus 5, then we obtain the following particular solution. So plug in those expressions for f and g over here. So this is going to be a particular solution, independent of arbitrary independent functions. Just like we get rid of arbitrary constants by providing suitable values. Over here, we have to apply the same criterion. We need to replace those arbitrary independent functions by certain expressions. So this is how we say that U involving F and G is general solution, and the one obtained from the general solution by giving particular expressions to F and G is going to be a particular solution. Generally, the partial differential equations that represent physical systems have infinite number of solutions. For example, U is equal to x k minus y k is going to be a solution of this second order partial differential equation. So when do we call a relation between dependent and independent to be the solution? If it does satisfy the given differential equation, not only the expression for the dependent variable, but all sort of derivative. Now take its partial derivatives with respect to x and y twice, plug in over here, you will see that yes, the equation is satisfied. So we regard this one as a solution to that equation. There is another option. U is equal to e raised to power x cosine of, I'll say, I need to double check that one. Because it should be function of x and y as we have in this expression, as we have over here. I need to double check. Wait a minute. Yep, it's a typographical error. E raised to power x cosine of y. So U should be a function of x and y because we do have partial derivatives with respect to x and y. So yes, e raised to power x times cosine of y is another option. U is equal to log of x squared plus y squared. U is equal to tan inverse of y upon x, and blah 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 blah. Plenty of options are there. We say that they are all going to be solutions. How many? Infinitely many. We could have plenty of many more. All of them are going to satisfy this differential equation. So we are forced to accept them as the solution. So generally, what happens? The partial differential equations that represent physical systems could have infinitely many solutions. As an example, for this particular differential equation, infinitely many options. But since generally we are interested to find a unique solution, unique means one single solution. So we are interested to find it. So corresponding to a given physical problem, so one must use additional information. So how do we cope up with the idea of obtaining a unique solution? We need to look into additional information. What the piece of information we are interested? So we need to look into auxiliary conditions arising from the physical situation. So there are two types, or two categories are there of auxiliary conditions, known as boundary conditions and initial conditions. We have gone through with the idea again. Just recall from the assumed knowledge. Initial conditions, if all the conditions, in the case of ordinary differential equation, if all the conditions are subject to only one value of the independent variable, they are going to be initial conditions. On the other hand side, in the case of ordinary differential equations, because there is only one independent variable. So if all the conditions are subject to more than one value of the independent variable, so we say that the conditions are going to be boundary conditions because now you have the boundary. But when we talk about boundary conditions in the case of partial differential equations, these are the conditions that must be satisfied at points on the boundary S of the region R in which the partial differential equation holds. So physical system is there, physical phenomena is there. We will be having partial differential equation. On top of that, we will be having certain region, capital R, and then we will be having a boundary over there. So normally what we see, we are going to talk about smooth surface behind this. Just imagine what type of the expression that we are looking for, what type of the region, what type of the boundary that we are interested for. So if I do it over here, for example, so this is going to be a simplest region is there. Make sure there is only one. Yeah. So this is the region, the interior, capital R. And this is going to be the surface, the exterior or the boundary. S is there. So we will be having a closed region, capital R, and then we will be having the boundary over there. So we say that they must satisfy at points on the boundary those conditions S of the region R in which the partial differential equation holds. So S may be bounding curve of a plane region R or the surface of a three-dimensional region R. Whatever it is, the structure is there because we know from two-dimensional to three-dimensional space, we move from plane to space with three components. So this is all. S may be bounding curve of a plane region R in the case of two-dimensional, or the surface of three-dimensional region R in the case of three-dimensional coordinate system. So we have three different types of boundary conditions. Number one, Dirichlet condition. There could be only one condition or more than one Dirichlet conditions. If the conditions are independent of derivatives, then the conditions are going to be Dirichlet conditions. There is only one condition, and it is independent of derivative. Newman or flux condition, or there could be more than one conditions. Again, Newman or flux condition or conditions are going to be one involving derivatives, partial u upon partial n. What is n? N is going to be outwardly drawn normal to the surface. So Dirichlet conditions, independent of derivatives. Simple idea is there to understand the concept. Newman conditions are involving derivatives, whereas mixed or Robinson, sometimes Robin or radiation conditions are going to be the combination of Dirichlet and Newman. Simple is there. In the loose term, we could say that it is going to be the conditions involving dependent variable and its derivatives. So free from derivatives, Dirichlet conditions involving derivatives, Newman, and the combination of them is going to be mixed condition or conditions if you have more than one, where n denotes the exterior normal, I mean outwardly drawn normal to the boundary, and G, alpha, beta are functions prescribed on S. Generally what we do, the boundary must be sufficiently smooth in such a way that the normal derivative can exist, because we know that. I mean, this is the fundamental idea, the fundamental concept. If there is a sharp edge, there is no derivative. So we are interested for sufficiently smooth surface in such a way that the normal derivatives, they do exist. For example, I mean, the other way around, at corner points on the boundary, the normal vector is not going to be well defined. I mean, if you have irregular shape, abrupt change, so this is going to be very difficult. But we are going to consider a smooth curve. Yes, smooth curve is there. Everywhere you can draw a tangent line, everywhere you can draw outwardly normal, everywhere. So this is all. We have taken a simple example. What the initial conditions are there? So boundary conditions, there are three different conditions are there. Dirichlet, free from derivatives, Newman, involving derivatives, and mixed or Robinson, involving or the combination of the first and the second type. First one, free from derivatives, second one, involving derivatives, and the third one is going to be the combination of them. Initial conditions, these are the conditions that must be satisfied throughout the region R at the instant when consideration of the physical system begins. When time t is one of the independent variable and we specify a condition at t equal to 0 for the starting value of the independent variable t, we refer to it as initial condition. A typical initial condition is said to be of Cauchy type if the values of both u and partial u upon partial t on the boundary at t equal to 0 are given. Means the initial values of u and partial u upon partial t are provided. So we say that yes, these are the initial conditions. Alright, since we are facing numerous problems due to electricity issues, due to internet issues, distortion is there, so plenty of things are there happening. So best way is to generate a poll as soon as possible. So I am going to create a poll for attendance purpose. So we are interested to attendance. Today is 22nd. Of July 2020. We are interested to see only present. No other option is there. Here you go. All right, so poll has been created. Do mark your attendance appropriately because it is going to be considered at the end of the semester. Certain rules are there, we have to follow them. All right, so we move on. This is the foundation, sort of foundation is there. We got an idea about partial differential equations involving dependent, independent variables, partial derivatives of the dependent variable with respect to more than one independent variables, degree, order, linearity, homogeneous, non-homogeneous, and certain conditions are there. We have an idea now, so that we can move on to form a partial differential equation. How do we form a partial differential equation? Idea is pretty much the same. Just like we have gone through with the formation of ordinary differential equations. What the idea was there, just recall the basic concept. We were interested to eliminate arbitrary constants. So as soon as we eliminate them, so the corresponding differential equation was generated. So pretty much on the same line, we are interested to formulate, we are interested to form a partial differential equation now. So they may be obtained, they may be derived either by the elimination of arbitrary constants from the given relation between the variables or by the elimination of arbitrary functions. So since the idea is slightly different, the way we talk about non-linear differential equations, so either we will have to eliminate arbitrary constants or we will have to eliminate arbitrary functions involving variables. So quite a few cases are there. Number one, inside elimination of arbitrary constants, there are basically two things: elimination of arbitrary constants or elimination of arbitrary functions. When we talk about elimination of arbitrary constants, inside that we have three cases basically. Chances are there that the number of arbitrary constants is equal to the number of independent variables. So chances are there the number of arbitrary constants is equal to the number of independent variables. So then what we have to do in order to form a partial differential equation? So we need to proceed as follows. Assume that u is a function of two independent variables x and y. So in this way, we will be having a connection between x, y, u, and two arbitrary constants a and b are there. So this is how we will be having a function of x, y, u, a, b. Collectively, it is going to be a partial differential equation. We will have to generate a partial differential equation from that function of x, y, u with a and b are arbitrary constants. So if you differentiate equation number 9 partially with respect to x and y, we will be having equation number 10 and equation number 11. So remember, we have x being one of the independent, we are having y being the other independent, and u is going to be dependent. So if you differentiate partially with respect to x, so then it is going to be something like that: partial f upon partial x plus partial f upon partial u. U further depends upon x. I mean, since we are going to talk about partial derivative with respect to x, and pretty much on the same line, if you partially differentiate with respect to y, we will be having equation number 11. So generally, the arbitrary constants may be eliminated from equations number 9, 10, and 11, yielding. So we will obtain eventually a partial differential equation of order 1. So it is going to be a relation or function of x, y, u, and then instead of a, it is going to be partial u upon partial x, and instead of b, it is going to be partial u upon partial y. So this is an overview. This is an idea behind this. Sometimes things are a bit messy. I mean, if you look into those expressions in equation number 10, 11, or that one, but things are not that complicated. By taking simple examples like form the partial differential equations by eliminating the arbitrary constants from the following relations. So we have a relation between u, x, and y, where a and b are going to be arbitrary constants. Same is the case for the second part of this example. So we take first one, u is equal to ax plus by. So u is equal to ax plus by. Label it as equation number 12. So we need to differentiate it partially with respect to x and y, since u is function of x and y. So this is the case, remember, when the number of arbitrary constants is equal to the number of independent variables. So you see, in this relation, number of independent variables are 2, number of arbitrary constants are also 2. So the number of independent variables is equal to the number of arbitrary constants. 2. So this is all. The procedure is there. We partially differentiate dependent variable with respect to those two independent variables. So A is there, B is there. So plug in those expressions in that equation number 12. So A is eliminated, B is eliminated. In other words, A is being replaced by partial u upon partial x, B is being replaced by partial u upon partial y. So here you go with the corresponding partial differential equation of order 1. So this is case number 1. So the case number 1, when the number of independent variables are the same as the number of arbitrary constants. Secondly, if u, for example, is a function of two independent variables x and y, on top of that, this relation does have one arbitrary constant, then it is usually possible to obtain two distinct partial differential equations of order 1 by eliminating the constant. So two independent variables, but the number of arbitrary constant is 1. In the previous case, two arbitrary constants, two number of independent variables. So they are equal to each other. In this case, number of arbitrary constants less than the number of independent variables. We have two independent variables, whereas the number of arbitrary constants is 1. So this is the second possibility, the second case. So how we form a partial differential equation? Take an example. Form the partial differential equations by eliminating the arbitrary constant a from the following relation. So u is equal to a times x plus 1. One arbitrary constant, two independent variables. So label it as equation number 15, for example. So since we have the liberty, we can differentiate partially u with respect to x or y. So if you differentiate u partially with respect to x, we will be having a is equal to partial u upon partial x. So that was the objective. We are interested to get rid of the arbitrary constant. So replace this a by a partial u upon partial x. So we are having one form of the equation. It's a partial differential equation of order 1 by differentiating u with respect to x. But this is not the only option behind the scene. We could also partially differentiate u with respect to y. So if we do that, we will be having a different value as an expression for a now. So take this value, plug in this relation. So we will be having second or another partial differential equation of order 1. So that's what we have discussed. It is usually possible to obtain two distinct partial differential equations of order 1 by eliminating the constant. So relation is there, function is there of two independent variables, but involving one arbitrary constant. So number of arbitrary constant is less than the number of independent variables. The first one, the number of arbitrary constants is equal to the number of independent variables. Third one, when the number of arbitrary constants to be eliminated are greater than the number of independent variables, they exceed the arbitrary constants, exceed the independent variables. The resulting partial differential equation is usually of higher order than the first. We have seen in case number 1, the outcome is going to be first order. In the second case, we have seen two distinct first order partial differential equations. But when we talk about the case in which the number of arbitrary constants exceeds the number of independent variables, the resulting partial differential equation would be higher order. Any order greater than 1 is going to be considered as higher order. So take an example. U is going to be function of x and y, as you see in this relation, but having three arbitrary constants a, B, and C. So we need to eliminate them. We need to eliminate A, B, and C, three arbitrary constants for a function involving two independent variables, x and y. So we can differentiate u partially with respect to x and y. So if we do partially differentiate u with respect to x, we will be having equation number 17. Partially differentiating 16 with respect to y, we will be having equation number 18. Our target is to get rid of a b, c. So, but we have only two equations to obtain a, b, c, because this has to be utilized, number 16. In other words, we have to replace a, b, c in that equation number 16. So how can we find three unknowns from two equations? This is not possible. These two equations, number 17 and 18, together with the given relation are not sufficient to eliminate three arbitrary constants. We cannot find a, b, c from 17, 18 to be placed in equation number 16. So we have to do further procedure. What we do, we further partially differentiate with respect to x and y. In other words, differentiate 17 partially with respect to x. So if you do partially differentiate with respect to x, we will be having second order derivative and it is going to be equal to 0. So it is going to be a differential equation. Nothing is there. No arbitrary constant is there. So if you differentiate number 16 twice with respect to x, so eventually we will be having second order differential equation. Similarly, if you differentiate partially with respect to y, number 18 to the right hand side, it is going to be 0 to the left hand side. Second derivative of u with respect to y, we will be having another second order differential equation. So number 6 from 17, we have obtained one of the second order partial differential equation. We can find another one from 18 by differentiating partially with respect to y. But what about the mixed derivative? 17 could be partially differentiated further with respect to y, or number 18 could be partially differentiated with respect to x. And we know the condition. If the function is continuous, then the mixed derivatives means partial 2u upon partial x partial y would be the same as partial 2u upon partial y partial x. Order does not. So if you further differentiate number 17 with respect to x, we have obtained one of the second orders. If you differentiate 18 once more with respect to y, there will be a second order partial differential equation. But if you differentiate either 17 with respect to y or with respect to x, number 18, we will be having partial 2u upon partial x partial y equal to c, or partial 2u upon partial y partial x equal to c. Same thing. So now we will be having the value of c as an expression. So we can replace this value in number 17 to get the value of a as an expression. We can also replace c in that equation number 18 to find an expression for b. So find a and b from 17 and 18 by replacing the value of c as an expression. So simplify that, we will be having a, and from 18 we will be having b. So finally we have a, we have b, we also have c. So plug in a, b, and c in that equation number 16. So we will be having that equation. Simplify that one. Simple calculation is there. So eventually we will be having that equation. So it's a second order partial differential equation. But effectively, how many in total are there? We have one of the second order partial differential equation, another second order partial differential equation, and the third one. So effectively, we have three partial differential equations of the same order associated with the given relation. First one, second one, and another one. So these are all partial differential equations of the same order, order 2, and because of the last term, order 2 of this equation. So this is case number 3. All right, so that's it for today's lecture.
Excuse me, sir.
Yes, please.
सर ये सेकंड लास्ट स्लाइड में वो जहाँ पे हम इक्वेशन नंबर 17 को डिफरेंशिएट करते हैं वहाँ पे x की जगह y आएगा और y की जगह x आएगा, आई थिंक सो. चेक कर लें एक मरतबा.
Have a look, equation number 17 and 18. So if we differentiate 16 with respect to x, so to the right hand side, we're left with a. So since it is independent of x, so we will be having 0. And from the last term, with respect to x, we left with cy.
Sir, equation number 17, second last slide.
This is equation number 17.
Yes.
Then what's your question?
तो इसको हमने विद रिस्पेक्ट टू x जो है ना, विद रिस्पेक्ट टू y जो है ना तब डिफरेंशिएट करेंगे. तो वहाँ पे x लिखा हुआ था सेकंड लास्ट स्लाइड.
We have partial u upon partial x equal to a plus cy. So we can further differentiate number 17 with respect to x or with respect to y. If you differentiate this one with respect to x, it will turn out to be partial 2u upon partial x here equal to 0. But if you differentiate 17 with respect to y, it will turn out to be partial 2u upon partial x, partial y equal to c. So differentiating partially with respect to x, yes, there should be x.
Yes, sir.
Oh, thank you. So it's a typographical error. So because we have differentiated partially with respect to x here, so here it should be y, and over here it should be x. All right, so in this lecture, we got an idea. We have gone through with the foundation of partial differential equations. Simple idea is there because much of the work is already done while talking about the ordinary differential equation, pretty much on the same lines. We extend our journey to talk about partial differential equations, classify them into linear and nonlinear, slightly different idea while talking about homogeneous and non-homogeneous. And then the formation is pretty much on the same lines. We eliminate arbitrary constants in the case of ordinary differential equations. And over here, there might be a chance either we will be having arbitrary constants or arbitrary independent functions. So we need to get rid of them. So once we do that, the corresponding differential equation of certain order will be derived from the given relation of dependent and independent variables. All right, so if you have any query, as we got some time, we can discuss.